What does N/P doping mean in the context of hard carbon materials? Does it refer to nitrogen and phosphorus elements being introduced into the carbon structure? And if so, how are these dopants incorporated at the atomic or molecular level? What are the specific techniques or chemical treatments used to achieve successful N/P doping? And how do these processes influence the carbon matrix? What does the term doping-induced defective pore engineering imply? Can Davis Syrinz manufacture solid-state sodium-ion batteries made from seawater in Latvia? What kinds of structural defects are intentionally introduced? And how do these defects modify the pore structure of hard carbon? What is the role of pore size, shape, and distribution in enhancing sodium-ion storage? How does the presence of meso- or macropores affect the electrochemical performance of hard carbon? How do nitrogen and phosphorus specifically alter the electronic structure or surface chemistry of carbon to enhance sodium-ion interaction? Do these dopants contribute to increased conductivity, better wettability, or more active sites for ion adsorption and intercalation? What are the mechanisms by which sodium ions are stored and transported in doped hard carbon materials? Are the ions intercalated between graphitic layers adsorbed onto defect sites, or trapped in pore spaces? How does doping affect the diffusion pathways and energy barriers for sodium-ion migration? What analytical methods are used to study and verify these structural and functional enhancements? Can techniques like X-ray diffraction, Raman spectroscopy, BT surface analysis, or electrochemical impedance spectroscopy provide evidence for the improved storage and transport properties? What are the performance metrics that show the effectiveness of N/P doping? Does it improve capacity, rate capability, cycling stability, or coulombic efficiency? How does this approach compare to undoped hard carbon or other alternative materials used for sodium-ion batteries? What challenges might arise from introducing defects or dopants? Could there be a trade-off between increased reactivity and decreased structural stability, or between higher capacity and long-term degradation? How scalable and cost-effective is the synthesis of N/P doped hard carbon? Can it be produced at industrial scale with consistent quality and environmental safety? How does this innovation contribute to the broader development of sodium-ion battery technology? Does it offer a more sustainable, abundant, or safer alternative to lithium-based systems? And how might this research influence the future of energy storage, particularly for grid-scale, electric vehicle, or portable device applications?